So good afternoon, one and all present here. So today we have this third sessions of today. So Dr. Sandeepan Dhar is going to take this session, and he is currently working as a researcher associated with Fraunhofer Institute of Integrated Circuit IAS, Germany. He has completed his PhD from NIT Durgapur, where his research focused on the speech synthesis using deep generative models. And his research interest lies as speech processing, deep learning, and generative AI, particularly in developing advanced model of speech synthesis and audio signal processing. Today, he's going to deliver the sessions on that. So, thank you. Now, session is yours, Dr. Sandeepan. You can take over.
Thank you, Dr. Satyaranjan Das sir. So let me share my screen. So one problem I can see is like if I have to play any sample from my local system, so the Chrome is not allowing me. So I have to play it from Google Chrome tab only. So those samples or videos that I have in my local system, I won't be able to play. But although most of the sounds, the playable sounds are there in my Google Chrome, so every time probably I have to switch or share the
No, no,
screen.
no
So
problem. No problem. You can.
yeah, yeah. So hello everyone. I hope my screen is visible.
Yes, yes.
So thank you so much. So as the title of my PPT goes, like generative speech synthesis from fundamentals to GAN and diffusion based models. So I will start from the very basics of fundamental of speech processing. I will not go very deeper because I believe that other speakers already covered that. But I will just go through the human speech production system, how it works, and then I will go through how neural network based models can help us to model a speech generation process artificially using deep neural network models. So this is how human speech generation system basically works. So whenever we have to utter any sentence or we have to convey any message to the world for communication, so what first thing we do is we formulate the message. So is the first part is called message formulation. Then is language code. That is the language in which we want to deliver the statement or the message that we want to deliver to the world. So the language code is the second part. At the same time, we also do language translation. That is sometimes mostly what we do is we think in our mother tongue, then we do translation, and then we deliver the speech. Then comes neuromuscular action. So this is the neuromuscular action is just a particular time when the brain basically gives signal to different parts of the different organ associated with the vocal tract or human speech production system, and accordingly different parts work. Then this is a sound source. So whenever we want to speak something, so flow of airflow comes out from our lungs and it passes through our oral cavity and nasal cavity. So we'll go a bit deeper into the oral cavity and nasal cavity in the later slides. So you can think of like, so it starts from this lungs, the airflow comes through the this vocal tract, and then based on the shape of the vocal tract, different phonetic sounds we can make. So any speech we utter is basically comprised of very fundamental sounds and called as a phoneme. Then comes the listener. It is basically associated with speech recognition system. So this is the speech generation system, and then comes the speech recognition system, which is also very important because when you use different AI models to generate speech, we must have to evaluate the quality of the speech, natureness of the speech, and for that purpose, we are highly dependent on the subjective evaluation. That is the evaluation that takes place using human subjects. So that's why we must have to have some idea about how the speech recognition system also work for human from human perception. So when this acoustic wave hits the our eardrum, then we have something called basilar membrane. So what it does basically, there are some hairs which is particularly get response from the different frequencies associated to the speech, and then our brain can decode the content, and then we understand the whatever is being uttered by the speaker. So this is the exactly what I wanted to mean, this oral cavity and nasal cavity. So whenever we uttered or you try to utter any speech through the vocal cavity, the air flows and it passes through the oral cavity and nasal cavity. So as you can see, this is a static cavity. This doesn't get changed. However, this oral cavity basically gives shape to different puffs of air that coming out from the our vocal tract, and based on the shape of or the place and manner of articulation. Place of articulation is exactly where the articulation is taking place, and manner is how it is being transformed. How our vocal tract is transforming the particular sound. So based on the place of articulation and manner of articulation, different phonetic sounds are being made. So this is basically dynamic cavity, and it does change based on whenever we utter a specific type of sound. And then comes the very important part, which is basically responsible for making these voice sounds, is the vocal folds. So vocal folds vibrates whenever we want to make a specific type of phonetic sounds, primarily the voice sounds, like e, o. So that is how the vocal tract actually vibrates, and different sounds we can make, and at the same time we can make our pitch high and low based on the, the how frequently the vocal folds are, this vocal folds are closing and opening. So I would like to share one video which make you understand.
Normally, you have a clear voice.
So as you can see over here, the continuous closing and opening of the vocal fold, and then this vibration takes place, and we can hear different sounds. I guess you cannot hear the sound because I cannot share this playable sound from my local system. However, you can see the how the vibration takes place.
No, we can listen.
Okay, then it's great. That's good.
Use a chest voice and belt it.
And let me show you the MRI of vocal tract, how different part of our vocal tract is basically helps us to make different kinds of sounds.
Speech production is possibly the most complex of human behaviors. In 1 second of fluent
So as you can see that this part is nasal cavity is static, it is not changing over the time, but this oral cavity is continuously changing based on whatever phonetic content or basic fundamental sounds we are trying to make.
we can produce approximately 5 or 6 syllables comprising 10 to 12.
And based on the place and manner of articulation, we can even divide the fundamental sounds in different categories: voiced, unvoiced. Then again, there is I will show the category based on the IPA, the International Phonetic Alphabet. And all these things are very much important for speech generation process. So when you do text to speech synthesis primarily, or so let's say singing voice synthesis, we must have to have a basic idea about this IPS, International Phonetic Alphabets, and because we convert the textual transcript into its corresponding phonemes, and then we expect the model or AI model or deep generative model to learn the mapping of phone to corresponding acoustic features. And this is how we can hear the sound and we can recognize the content of the speech. So as I was mentioning that we have this our cochlea. So inside the cochlea we have this basilar membrane. So inside this basilar membrane we have these different hairs, and each of this is basically can respond to different specific frequency from lower to higher frequency range. And then we have this auditory cortex, which is basically responsible for decoding any content of speech. And this is how I'd like to explain at the same time, what analysis synthesis process basically works in human speech processing system. So as I have just mentioned with the video that whenever we want to utter any speech, basically the initial thing is like airflow, which comes from the lungs, and we also call it the excitation signal. Then it passes through the oral cavity and nasal cavity. So this oral cavity, as I mentioned, that it's a dynamic you can map it as a dynamic function, which keeps on changing based on the content of the speech. And then this is basically also called as a transformation function, because it's transform this puffs of air that coming out from the lungs. and then we get the final speech. So it is in a time domain. So as you can see, it is basically the convolution between this response of these excitation signals, and it is a time delay. This transformation function is mentioned over here is a time delay function. And if you take the in discrete domain the frequency domain transformation, then you can see that this is a continuously decay function, this excitation signal, and then when it can multiply with this response of the vocal tract or transformation function, then we get the final. In the frequency domain, this is what we can get. So this is the x of omega. This is the final speech, and it is frequency domain transformation, which basically you can see that it's a periodic property is coming from this vocal tract response function, and this is the excitation signal is basically responsible for the energy associated to the speech. Then the question is how mathematically you can design this, or mathematically you can understand the frequency component associated to the speech. And for that purpose, we have this different algorithm associated with the speech processing, and I guess it is already been covered in the previous talks, or maybe in future talks it will be covered. So I'm just giving you the basic idea about. So when we visualize any speech, so we actually get the time domain representation. That is, with respect to time, how the amplitude is getting changed. So it gives an idea about the loudness associated with the speech. So whenever you play any sound, in different applications, when you play the sound, you primarily you see how with respect to time your amplitude is getting changed. It basically gives an indication about the loudness associated with the speech. But if you want to check how the frequency is changing over the time, then we need this spectrogram. So before that, we need to do Fourier transformation, that is frequency domain transformation. So as you do the frequency domain transformation, so you get an idea about which is this most prominent frequency associated with the speech. So this is the Fourier domain frequency domain transformation. So as you can see, say for example, in this speech, when you see it from this direction, you do not get an idea about how many frequencies are associated with the speech or forming this speech. But when you do this Fourier transformation and you visualize it from this direction, you exactly get an idea about which are the prominent frequency associated to each, and also the magnitude of each of the frequencies. But it doesn't give an idea about how these frequencies are changing over the time, which is very important, because we want to understand how the frequency is changing with respect to time, that is the content of the speech. So for that purpose, we have the spectrogram. So how we can get the spectrogram? So first of all, we do short-time Fourier transformation. So we divide the whole time domain signal into a small window, and then we do the short-time Fourier transformation. So after doing the short-term Fourier transformation, we get the frequency and is the corresponding amplitude, or the contribution each of the frequencies in small time interval or the window that we have taken. Then we just do the transformation of this anticlockwise, and then we club all this together. So what happens when we club all this together? In the x-axis we get the this time frame, and in the y-axis we get the frequency domain information. So this is how the spectrogram is formed. So you get this how with respect to time these frequencies are changing. So this is one view. So as you can see over here from the male spectrogram or the spectrogram, what we can do is we can see this how with respect to the time this frequency is changing, and as you can see it is forming some kind of a continuous a curve. So what this continuous curve basically is. So for that purpose, I'd like to go to the second slide. So say for example, this is a very periodic signal, and for any periodic signal, once we do this Fourier frequency domain transformation, we get the information associated to the frequency associated to the particular speech. Now there is something called fundamental frequency, the most prominent frequency, and in the most prominent frequency, the energy is highest. Then if you multiply this fundamental frequency with this constant multiple, then you will get the harmonics associated with the frequency, but the energy is continuously decaying. So that's the reason when you get the spectrogram or main spectrogram in the lower frequency range, you get the highest energy. Most of the energy concentrated on the lower frequency range. This is where the fundamental frequency exists. As you go up, then you get the harmonics associated with the frequency, but energy keeps on decreasing. So this is basically the reason why in the this curve we found that this plot, I mean this lines are basically quite brighter as compared to the, and it is completely missing in the higher frequency range. Then something called formants. So what exactly formants are? So if you think the vocal tract as a tube, and based on the shape of the this of the sinusoidal wave, we can, and I mean we can find a relationship between this length of the vocal tract and the frequency. So based on the shape of the vocal tract and the length of the vocal tract, uh, we can model that, or we can understand that some of the frequencies become, I mean, it amplified by the our vocal tract, and these frequencies are called resonance frequencies. So these are this property of resonance frequencies. Some of the frequencies get amplified, and then they form kind of structure, and we call it the formants. And it also has a relationship, though, as I was mentioning, that the length of the vocal tract has a relationship with the frequency. So if the frequency, I mean, if the vocal tract length is high, then your frequency will be less. And if the vocal tract length will be short, then the frequency will be high. That's the reason why for children's you can hear their pitch is quite higher, or it is similar to female speaker, and for male speaker it is quite lower. And this is the formants. Formants and harmonics are not exactly same. So as you can see, this straight horizontal lines, yellow color lines, these are basically harmonics, and these red lines which is forming the formants. And then I like to show how these formants actually we can associate to the content of the speech. Now, say for example, we have uttered three words: machine, father, and school. So in machine, E, the sound E, we can visualize it is spectrogram. And similar time, A, father, fa, A, we can visualize the spectrogram, and also in school, U, the sound U. So as you can see in machine E, this sound E, fundamental sound E, and this is IPA. So this is how we represent this fundamental sounds. So we have different IPAs for different languages. With the help of this IPS, we can distinguish different kind of fundamental sounds. Now, as you can see over here, for this sound E, the first formants is coming somewhere here, and the gap between the first and second formant is quite higher, and second and third is appearing the, I mean, closer. Then for the sound fa a, this is again different. Now first formant and second formant is closer, and from second to third there is a high distance. So based on how the different phonetic sounds are forming different formants, and what is the range of the frequencies, we can distinguish or identify different phonetic sounds. So as you can see, if you plot in the x-axis and y-axis using just two formants frequency range, then we can simply identify different phonetic contents associated to the particular speech. And then I have already mentioned that you can distinguish in multiple more categories like voiced, unvoiced. Then based on the how you are making the sound, say for example, some sounds like this. So where it is not vocal tracts is not vibrating. Then we have this vowel sounds, as I already mentioned over here. So based on this place of articulation, manner of articulation, we can also distinguish in multiple categories. Then this is up to what we have understood, that how we can analyze or you can understand the speech is, based on the speech processing technique, that in terms of its corresponding features. So first we obtain the waveform that is in time domain, and then we do this frequency domain transformation. We get the Fourier transformation, and then we get the spectrogram using this logarithmic transformation. I'm doing STFT, then logarithmic transformation. Then there's something called Mel filters. That is how we perceptually hear the sound. So I'm not going to it very deeper into the male spectrogram. So you can think like that in lower frequency range, human ear can very easily distinguish the frequencies. Like say for example, in music, if you listen to the notes sa re ga ma pa dha ni sa, so if you are asked to pronounce or sing the note re, and instead of that you are somehow making the sound like sa, then it our human hearing perspective, we can very easily distinguish, okay, the pitch is not correct, the pitch should be correct, it should be lower or upper based on the which sargam you are asked to sing. But when the frequency is quite higher, say for example 1000 2000, then it is the closer frequency cannot, I mean, you cannot very easily distinguish. So based on then male filters has been designed. So male filters basically transform the frequencies again based on the human hearing perspective, and thus you call this male spectrograms, log male spectrogram, if you do the logarithmic transformation on the male spectrogram. So now we can get an idea about how we can understand the content of speech just looking at the spectrogram. So it basically comprises of multiple these phonetic sounds, and if you combine all the phonetic sounds, then we can understand that how the formants are changing over the time. And let me show you one plot using Parat like this. So say for example, this is the let me play it.
मैं जीवन की राह में आगे बढ़ चला.
So मैं जीवन की राह में आगे बढ़ चला. This is the content of the speech, and then you can see that how this formants. So red colors are the formants, and the blue is the pitch. This is for the fundamental frequency, the most prominent frequency, and it is the intensity, the energy associated to the each of the content. So that's the reason. If you analyze it in a time, in the axis, if you plot the time, then you can very easily understand how the pitch, formants, energy is changing over the time. And you can also take small chunk of it, and you can visualize that. Yeah. So as you can see over here, this is basically the signal in time domain, and then we have the pitch corresponding to it. Then we have the formants, these red dot colors, and the intensity. So based on so we can also change this parameter. So this PRAT is specifically for the speech visualization of speech, and we have in Python library called Parselmouth. So it is the wrapper on this PRAT. So you can analyze or you can change the parameters. Say for example here, for each of the say for example pitch, intensity, formant, whatever you take, you can go to the advanced setting, and then you can change and you can analyze. You can, selection of this parameter is extremely important. So if you do not select the parameters appropriately, then you may not get a correct pitch or correct formants. So that's why you have to analyze the. You should be familiar with the PRAT visualization, and based on that, when you write the code in Parselmouth using Parselmouth, we can condition the function based on the parameters that you have selected from the PRAT. So it is specifically for the speech visualization. So this is so far we have understood. Now the question is how we can align this contextual information with the speech. So if you have the text corpora, there is the content of the speech is given to you. Say for example here, the content of speech is basically tumko, and you have the short utterance tumko in the time domain, and it is a pitch. Now the question is how we can understand if you break the word into its corresponding phoneme or syllables, the duration of the phone, how we can understand, how can align it. So this is exactly very important. But before going to that, we have to, I wanted to show you that when you have this content of the speech and the corresponding audio, our basic objective is to use some alignment algorithm and get the align the syllables or the phones. Then we can more easily analyze how for each of the phoneme, how the pitch or the corresponding information are changing. And this is the pitch associated with the specific phonemes, and this is a slur. Slur I will explain probably in the when I go to the slide of singing voice synthesis. As of now, the most important part is this alignment. Tumko Then we get the syllables and we get the phones, and we align this with the corresponding speech, and then we get an idea about the duration of the phonemes. So starting of the phone and ending of the phone, it will give the idea about the duration of the phone. But for that purpose, we need an alignment algorithm. So I guess I missed out the alignment algorithm on my last slide. Sorry. Yeah. So I have already written the alignment algorithm in my last slide. Sorry. So how we can align? I get the alignment algorithm. How alignment algorithm help us to align the phone with the corresponding frame? So first, as I mentioned, say for example, we have a sentence, then we must have to have a vocabulary. This vocabulary should contain for every word what is the corresponding phone. So say for example, here the cat sits on a mat. So you have the cat sits on a mat, and you have the corresponding phone. So you must have to have a dictionary. If you do not have a dictionary, you must have to use some phonemizer, like grapheme to phoneme or any existing phonemizer like deep phonemizer, eSpeak, iSpeak, Epitren, etc., etc. So there are multiple phonemizer who does the phonemization for you. Given the text and the word, you get the corresponding phonemes. But the thing is, like, here IPS has been used, International Phonetic Alphabet, but you may have to, you can use your own dictionary. Like IIT Madras have its specific phone set. So in many of our work, we have used this IIT Madras phone set. So based on which phonemizer you are using, or so which phonemizer you are using, you will get the corresponding phoneme information. Now, once you have the phoneme information, your second task is to align with the spectrogram or the spectral information you have. So primarily for this alignment process, we use this CALD framework, and the acoustic feature we use is MFCC. So first we get the speech, this audio data, then the transcript, the content of the speech, then we do the phonemization. After that, we extract the MFCC feature, the acoustic feature. So you can think like if we take very small window and say for example 10 milliseconds, so you get say for example x1 to xt, so t will be a very high number, so because you have multiple small chunks of 10 millisecond window. So then our objective will be to map the phone with the corresponding acoustic frame. So that's I mean, in case of HMM GMM based force alignment in CALD, how it does is after extracting the corresponding MFCC features, it assign hidden state to each of the phoneme. So say for example, you have a phone here for cat, KAT. So each of the phone will get corresponding hidden state. That is the starting of the phone, intermediate, and the last. So you will get for each of the phoneme the corresponding hidden states. Then this HMM will look after that. Before going to the HMM, let me explain what exactly Markov chain means. Markov chain basically indicates that if you have a sequence of information from x1 to xt at a particular time instant t, the t is completely dependent on whatever event has occurred just xt minus 1. Similarly, any future event at xt plus 1 will be completely dependent on xt. So that means it has a time in time domain, it has a relation with only its previous information or the event that took place just one time delay. One time before. So based on this concept, hidden Markov HMM hidden Markov models are assign each of the phone the corresponding hidden states, and then you have something called GMM, Gaussian mixture model. So if you can think of a unimodal distribution, Gaussian distribution, some like a bell curve. So then it has only one model. But if you have a multimodal distribution where you have a multiple such peaks, then we can think of multiple Gaussians. This is called Gaussian. So this is how Gaussian mixture model helps us to model such kind of distributions where we can we can assume this multimodal distribution comprise of multiple mean and standard deviation, and then using GMM we can approximate for a particular time frame which phonetic content it may belong. So based on the likelihood estimation, and then comes this Viterbi decoding. So what it does, it then again check whether the sequence has been maintained or not. So I'm just restructuring the things again. First, you get this audio, you get the speech, then you do phonemization. After that, for each phoneme, you get the corresponding hidden state, initial, intermediate, and final. Then you do you use the GMM algorithm, Gaussian mixture model algorithm, which basically gives you an idea about for a particular time frame which phoneme sequence it can belong. So instead of directly mapping it to the phoneme sequence, it basically try to map it to the hidden state of the phoneme sequence. Then after that, this Viterbi algorithm try to again check whether the sequence has been maintained or not. Then we get the final sequence where we have the corresponding phone or the hidden state and the corresponding acoustic frame. After that, we can get the information of the for each phoneme what is the corresponding duration. That is what I have shown over here. So I'm not going to very details about this GMM HMM alignment because it will again then take more time to explain all these things. But I'm just giving you an intro about all this algorithm that we use in speech synthesis, primarily in text-to-speech synthesis. Then another very important component in speech synthesis is the vocoder, the voice encoders. So what it does, so when we do speech synthesis, basically we map the feature from one domain to another. Say for example, if your mapping is like you have a male spectrogram associated to one specific speaker, and you have in the target domain another male spectrogram associated to another speaker, then your model is supposed to learn the mapping. This is something called voice conversion that I will cover in the next slides. Or you may have a textual transcript, just like what I have shown over here in my last slide. You may have the textual transcript and the corresponding acoustic feature, and your model have to learn corresponding to the textual transcript what is the corresponding feature, such that you can condition in the inference that given a new content what will be the corresponding acoustic feature. Now the problem is, once you have this spectral feature, let's say for example spectrogram or mail spectrogram, how will again get the speech in time domain? So for that purpose, you use the vocoders, and neural vocoders mostly used nowadays. Hi-Fi GAN is a very popular one. Then we have Big GAN, and then we have also statistical vocoder that we used to use in earlier days. Nowadays, it is totally we have switched to neural vocoders. It is neural network based vocoder. So as you can see over here, it is giving us some character embedding. I will explain it in later slides. Then it is expected to generate the corresponding male spectrogram, as it can be seen here. Then given the male spectrogram, it is giving you the corresponding or audio in the time domain. In case of statistical vocoder, what you used to do is to extract the different type of features. Say for example, the fundamental frequency F0, then APCTC is particularly associated to voiced and unvoiced information, and spectral envelope. Then you can change the the fundamental frequency or the spectral envelope shape, and you can get the corresponding audio. So this is how earlier days speech synthesis used to be done using the statistical vocoders. So I will show one demo where we have used this statistical vocoder, world vocoder primarily. So this is basically the idea about how vocoder is being done. Vocoder plays a very significant role in speech synthesis, the selection of vocoder. And so this is the basic idea, whatever I have so far explained, that you get the audio, then you do frequency domain transformation, we get the spectrogram, then we transform into male spectrogram, then we do mapping based on our requirement, whether it is text to speech in this model, whether it is a speech to speech in this model, and then finally you get the corresponding audio, the generated audio. Then these are types of speech synthesis. As I have mentioned that speech synthesis can be of different types based on what application we are working on. Like say for example, speech to speech, as the name indicates, the input is speech, output is speech. Text to speech, as the name also itself indicates that the input will be a textual transcript and the output will be a corresponding speech. Sorry, just I'm giving 2 minutes break. I guess someone has come. Just sorry, extremely sorry.
Okay.
Sorry. Yeah. So, anyways, what I was saying that this is the fundamental of speech tracing that is, I guess, already been covered, or it will be covered in other by the other speakers. So now I will be mostly focusing on the GAN-based voice conversion, text-to-speech synthesis, and diffusion-based speech synthesis, and then I will cover different types of domains, not only voice conversion or text-to-speech or singing voice synthesis. So as I was telling that voice conversion is a type of speech synthesis process, which is basically a speech-to-speech synthesis process where you give a speech and in the output also you get a speech. You do not give any textual transcript in between. So the idea in voice conversion is you have a source speaker. Now source speaker, say for example, uttered any content. Say for example, myself, Ravi. It is uttered by the source speaker. Then you have a target speaker. Say, for example, the target speaker is a known person, a celebrity like Amitabh Bachchan. You extract the corresponding vocal features from Amitabh Bachchan ji. Then your objective will be keeping the content as it is by the source speaker uttered, same as what source speaker utters. Just superimpose the vocal feature of the target speaker and generate the corresponding speech, such that it appear like Amitabh Bachchan ji is now uttering myself Ravi. So it is basically a synthesized speech, generated speech, not actually uttered by Amitabh Bachchan ji. So this is called voice conversion. So basically you are changing the vocal texture or identity of the speaker, but you are keeping the content as it is. So let us try to see some demo associated to this voice conversion task. I probably have to again share it. Yeah. So now, as you can see over here, the text is he is not perfect. So these are text. This is the content. So actually, you do not condition in case of voice conversion the model with any textual transcript just to show that what is the textual transcript. It has been shown over here. I mean, what is the content of speech? It has been shown over here. But in case of voice conversion, we do not explicitly give any content. So we expect that the model will itself learn the content related information, just change the vocal texture. Now, say for example, your source speaker is this.
He's not perfect.
And you have a target speaker.
I can't see him reversing that.
So it is a female speaker. So the idea is, in case of voice conversion, you will keep the content of speech as it is, just change the vocal feature as compared to as that of the target speaker.
He's not perfect.
So as it can be seen that now he is not perfect. This word is uttered by this target speaker instead of the source speaker. Similar to some other example.
The alibi is now gone.
By then, he was walking on water.
The alibi is now gone.
Yeah. So I guess you have understood the basic idea of the voice conversion. So it also, I mean, unofficially you also call it voice cloning, and mostly it is used in the dubbing industry. We ourselves have worked with one company, startup company, Mumbai-based startup company. I forgot exactly the name, Sound Engine or something. I just forgot his name. Anyway, so our objective was, so they used to do this voice cloning by their vocal artist, but the thing is, like, for that purpose, the vocal artist has to sit for a long time in the studio, had to spend a lot of time in the studio. So instead of that, what they did, they take the particular voice artist vocal texture, just they have in agreement with the artist, and instead of recruiting him for the whole time, what they did, they just take their the voice marker, as you can see over, I mean, instead of asking the voice artist to sit and utter the content for whole duration, they just took the permission from the vocal artist, and they already had the speech sample associated with the vocal this particular vocal artist. Then they have another speaker who is not that trained and his voice is not very familiar to the industry or with which they were working. Some serial, I remember some Marathi serial with which they are working. So the idea was like the unprofessional vocal artist whose voice is not very familiar to the industry, he or she will utter the content, and that will be replaced by the target vocal characteristics of the known vocal artist. So we did this project, but the problem was like we had to do it in real time. But so far the real time is extremely challenging, because when you use this voice conversion model, GAN based, diffusion based, these models, the inference time becomes quite high if you want to make it very robust or adaptable. So that is one challenging. So we could not address the problem of real-time voice cloning. But yes, voice conversion, so as of now, is very, I mean, it has well addressed by the people working or the researcher working in this domain. And now the generated samples that you will hear, it's very natural. So this mean opinion score is quite high. However, there are other challenges associated to it, like how we can retain the prosody. I will explain what exactly prosody is. Then zero-shot speaker adaptation, such that if you have a very less number of sample of any speaker, how you can adapt it, or at the same time making the inference time as low as possible. So these are the challenges that still exist. Now the question is how we do this voice conversion. So for that purpose, as I just mentioned, we have the source speaker, we have the target speaker, we extract the vocal feature related information. Then we train them, you deploy different models, different machine learning, deep learning based models. So for example, GAN, which try to map the vocal feature from source to target domain, and so then use the vocoder to resynthesis it in the time domain. So this is basically the idea of or the three-stage pipeline of voice conversion system. And voice conversion are of multiple types: parallel, non-parallel, monolingual, cross-lingual, intra-gender, cross-gender, one-to-one, many-to-many. So I'll just cover just basic overview of what it is. So in case of parallel voice conversion, we have the content for both source and target speaker. Parallel content means the same content uttered by source and target speaker. Now it becomes quite easy for the model because the parallel content is present. So if the model has to just learn vocal feature related mapping, then given a new content, we expect the model will generate the corresponding speech in target speaker voice. In case of non-parallel voice conversion, we do not have exactly the parallel contents. So what we have to do is like we have to extract the phoneme level information. Then we have to map the model we have to use the model in such a way it can generate the corresponding phoneme related information, even if it is not perfectly mapped, and it's quite challenging. That's the reason. So what the basic idea is nowadays, how we do, we keep some parallel information related to the source and target speaker. Then we map using the parallel content, and then we try to model that given an non-parallel content, how it will be able to generate the corresponding speech. So basically, non-parallel voice conversion means you do not have the aligned information. So it can be multilingual as well, because multilingual basically means that you won't have the aligned information. So this is what cross-lingual is multilingual, and monolingual means we have the same language information. And intragender out and the cross-gender that I have already mentioned, that if you have a source from one gender and target from another gender, then primarily their speech-related information. The speech-related information would get changed. Then another problem statement is how we can retain the prosody-related information. We do not want that the prosody gets changed when we are transforming the target speaker vocal texture related information. So what exactly prosody means? So as I mentioned, there is something called fundamental frequency that changes over the time. Now every speaker for a particular content, they have the corresponding fundamental frequency. Then their speaking rate, there is a number of phoneme utterance they make per unit time. Then the loudness or the energy associated with the particular speech, or the timbre of the speaker, how it has been spoken. So all these things basically associated with the prosody. Now, when we change the speaker identity, we do not want that this prosody should get altered completely. So that is one of the constraint in case of voice conversion, how we can retain the prosody related information as same of the source speaker without, by changing the target speaker identity. The source speaker identity. That is, just change the identity of the source speaker as that of the target speaker without changing the prosody related information. So I guess in this demo, these things has been shown that, say for example, you have the pitch and energy that is basically associated with the prosody. Keeping the prosody as it is, how we can change the speaker identity. Then we have one-to-one and many-to-many voice conversion. As the name indicates, in case of many-to-many voice conversion, you will be having multiple source speaker, multiple target speaker, and in the inference stage, you will be conditioning the decoder that given the particular source speaker speech, I want the target speaker as any of the target speaker by giving their label. Now, the present works on voice conversion, in the case of present work or preceding works in voice conversion, people are trying to do zero-shot voice conversion. That is, they do not want that the model should get trained only for specific target speakers. Instead, whether we can use some model using which we can make it zero-shot. That is, given a new speaker, it will extract the corresponding speech features and it can directly condition the model to generate the corresponding speech instead of explicitly train the model with some source and some target. And these are some application of the voice conversion. As I have already mentioned that in media industry, this voice conversion system are used for. Then in media industry for accent conversion also it is used. Then it also has an application in medical speech. So people who is suffering from what is called laryngectomy. So what happens? Their laryngeal part are being cut out. Then they cannot exactly speak, because as I have shown that when you, the speech is basically a combination of, it is basically a convolution operation between the excitation signal and the vocal trait response. So if you remove the vocal glottal impulse, glottal excitation signal, then it won't be able to vibrate, it won't be able to make the corresponding sound. So for vibration, they use this particular device which gives the vibration, and then they have this vocal trait response. So some sounds are being made by those kind of laryngeal patients, laryngectomy patients, and however the sounds are not very natural. So there are some voice conversion works that it's been done where the researcher tried to convert the this output of the laryngectomy patient's speech to natural like speech by considering other speaker. Then this is a very important type of voice conversion. How do you use this? Phonetic posterogram. So what it basically is, so as I have mentioned that it is very much important that you get an idea about how with respect to different time frame the phoning informations are changing. That means you must have to have a aligned information of phone such that you get an idea about how the acoustic feature associated to it is changing. Then only your model can understand and model can train, and in the inference you can expect that given a new phone and its corresponding duration, it can generate the corresponding speech. So for that purpose, we have something called phonetic posterogram. So what it basically has, you have in the y-axis all the phonemes, and in the x-axis you have the time frame. Then for each time frame, the black color indicates the probability of the particular phoneme. So you get an idea about at particular time frame what is the highest probability associated to particular phone. So then it can be said that the particular time frame belongs to that particular phoneme. So then we can use this phonetic posterogram to condition the voice conversion models. So as you can see over here, we have this ASR model. From ASR model, we can get the PPG, phonetic prostogram, that is the phoneme information, and how the with respect to time, how this phonetic information is changing. Then we can use different models, say for example, the world vocoder to extract the speech related information, voice and voice information. Then we can train the model to generate the corresponding speech. So once it has been trained with the target speaker, we can just extract source speaker content related information, these PPGs, how the phones and the durations are changing, and then we can generate the corresponding speech in target speaker voice. So this is basically the idea of PPG based voice conversion. Then another is vector quantization based voice conversion. Then I'll go to the GAN. So these are the PPG and vector quantization is also very important, because nowadays we do not work completely on GAN or diffusion. We do work on hybrid models like diffusion GAN, VK, vector quantization VAE GAN, VQ VAE GAN. Then we also use PPGs for non-parallel voice conversions. So that's why I just wanted to cover this part. And VAE is very much important, because if you go to the GAN-based voice conversion and then diffusion, you can relate it to the VAE. So what happens in case of VAE? You have the source domain. You use an encoder. Okay, let me just give you one small. Yeah, with my open board, let me just explain it. Won't take much time. So say for example, you have a source domain X and target domain Y. You can think of like audio data, speech, audio data, image, video, whatever. Now the idea is you use encoder model. It primarily convolution models, convolution neural network models. So what it will do, it will convert it into a latent representation, lower dimension representation. Say for example, Z. Now your X, say for example, is a higher dimension representation, capital X multiplied with capital Y, and this will be a lower dimension representation. Say for example, small x, small y. Now from this latent representation, you will again use some decoder. It will take this latent representation and generate the corresponding output. Say for example, y hat. Now the question is, if you are giving x, how it will generate y? Then there comes something called variational autoencoder. If your domain would have been same, x to x, then it will be only variational autoencoder. It is a kind of a deterministic process. But in case of generative process, you use the variational autoencoder. That means it learns the mean and variance. Then you can condition the decoder by changing the mean, by sampling the mean from different distribution, and then it can generate a corresponding output. Now it is expected that your y hat will not be very similar to y. It is expected. So then you use loss function or different divergence, probability divergence theories. Scale divergence is one of the popular ones to find the distribution difference between the two distribution, like y, the actual one, and the generated one, and accordingly the parameters will be get updated. Then once the model will get updated, then given a new mean and standard deviation, you can generate the corresponding output, which will map it to the domain y. Now the idea is, in case of voice conversion, your structural information associated to the x, that is the content related information, should not get changed. Only the distribution get changed as compared to the target domain. And for that purpose, VAE is widely been used. So what it does, as I mentioned, that it has some encoder. It convert into the latent representation. Then you have the target speaker code or some embeddings, and then condition the decoder, and it will generate the corresponding information. Corresponding feature. Then something So it is called VAE, but there's something called vector quantization. So what it basically does, you have a set of vectors instead of. So let me just explain it with this. Then it will be easy to understand. So as I mentioned that if your X, you are mapping it to a domain Z, lower dimension representation, then again Z with some decoder will map it to, say for example, the same domain XZ. So in this part, they use something called quantization, vector quantization. What is vector quantization? So say for example, your Z is basically something like time frame x1 to xt, and each time is time frame has dimension d feature representation. Then the idea is, instead of sending this Z over here, you use a big code book. Each code book will be having different entries, and you replace this vector with the nearest of the embeddings that present in this code books. Say for example, code book 1, code book 2, code book 3, so on. And then you just replace this embedding with the nearest one, and instead of sending the whole embedding, you can simply replace it with the indexes of this code book. So what it does, in case of vector quantization, the thing is like it after the quantization, using very less number of bit rate, you can send the data from one to another. So basically that is the reason why vector quantization is used. I'll explain it when I'll go to the audio codec part, neural audio codec part. So this is the basically idea. Instead of sending the whole dimension, you can replace it with some code book, and you can retain this code book with source and also in the target. And if you just replace, instead of sending the embeddings directly, which is in a floating point number, say for example for FP16 or FP32, you can send I'm getting some sounds. What exactly it is?
Questions are there from student side there.
Okay. Another thing is, I was changing my slide. Did you see the changes in my slide? Oh, so far I'm explaining to you. It didn't.
No.
Okay, you should have mentioned me before.
That's why actually they are muted. Okay. So they are writing in chat box.
Oh.
Just a 1 minute before only.
So I explained, I guess, so many things. Or can anyone tell me till when you have seen my slide?
Yes, you can unmute.
Up to the voice conversion, sir. After that, actually, it was not.
This one?
Yeah. After that, after this slide, no, we haven't seen this.
Oh, I have to re-explain this then. So if you see that any slide is not, I am explaining and you don't see the slide, then just let me know, because the problem
now
is
I am given permission to unmute. They can unmute and ask you till I have muted to all.
Okay. Yeah, so voice conversion, I guess I have explained. So this part is again what happens in case of voice conversion. If it follows 3-stage pipeline, that extract of source speaker and target speaker speech features, then it maps the In the training phase, it try to map the source speaker to a corresponding target speaker speech, and then in case of inference, we just condition with the target speaker voice features. So the idea is like the model is already been trained with the trained for the mapping. So given a new source speaker speech, it should be able to convert it to as per the target speaker speech feature. So basically, this is what exactly why I explained the last slide. And as I mentioned, there are multiple types of voice conversion, parallel, non-parallel, and let me explain over here. In case of parallel voice conversion, we have the same content uttered by both source and target. In case of non-parallel, you do not have the same content. So this is quite challenging. This is the reason why it is quite challenging, because we don't have a parallel content. Then mono and cross is basically the language identity get changed, and cross-lingual definitely means the non-parallel voice conversion. And then, as I mentioned, that the gender identity can be changed, and when the gender identity is changed, we expect that the models should also change the speech related information and energy related information accordingly. Because say, for example, a male speaker is uttering a content, then if you look at the pitch, that the ranges of the pitch will be lower as compared to if the same speech would have uttered by the target female speaker. Then we want the model to act accordingly. So in the voice conversion model, if you see that non-parallel voice conversion and cross-gender voice conversion is primarily what we try to address as properly as possible. And then one-to-one and many-to-many, as the name indicates, that in case of one-to-one, we just have one source speaker, one target speaker. For many-to-many, we have bunches of source and bunches of target speaker. And then in the inference, we also give which target speaker vocal feature we want in the generated samples. However, I have explained that we just don't give the, nowadays our basic objective is just don't train the model, hardly train the model for specific source and specific target. Rather make the model zero-shot voice conversion, zero-shot voice cloning, such that given a new target speaker and this corresponding speech of a very short duration, how we can extract the corresponding speech features and generate the corresponding speech. Then these are the different type of application of voice conversion, real-time dialogue conversion, then speaking style conversion. Then we have disordered speech conversion, where the patients suffering from laryngotomy, they're unable to speak appropriately like a normal speaker. Then you can use this device, which helps them to generate the corresponding. They just give it the acceleration signal. It works like an acceleration signal, and then the vocal tract change the shape the signal. Speech, and then different speech are being uttered. However, it doesn't sound very natural. And then there are in voice conversion community trying to address that how this kind of muffled speech or robotic speech can be converted to natural speech, taking the help of other target speaker vocal features. And this is the PPG, phonetic prosteogram, that I have just explained, where you have the information associated to the time domain in each time frame, which is the x-axis, and your y-axis is all the phonemes present in the speech. You get the probability of belongingness for each time frame, whichever is the highest probability of the phoneme. You can say that that particular time duration, that particular content time belongs to particular phone. So this is basically gives an idea of the mapping as compared to the time with respect to the time frame which particular phone it belongs. And then if you train the model accordingly, then it is expected that in case of inference stage, you just have to change the PPG if you want to change the content of the speech, and the model will change generate the speech in the target speaker voice. So then comes the GAN model. So what GAN does is basically, I guess I am already covered 1 hour. I'll skip. I will not go too much depth of it. So in case of GAN model, what happens? You have the generator, you have the discriminator. So unlike the VAE model, where you have one single model having the encoder and decoder, you convert the input speech into a latent representation, and then you use a decoder to generate the corresponding speech, and then you you try to find a difference between these two information, that is the reconstruct and the audio, using some KL divergence or loss function. In case of GAN, you separately deploy a discriminator, which is a classifier, to take care of this part, that whether the generated speech belongs to the target or real speech or not. Say, for example, you have the classifier which already aware of the DL speech or some target speaker speech. Then generator will try to generate new synthetic speech, and discriminator will keeps on discriminating or classifying that the generated speech is not like the original one. And this loss will get feedback, or gradient will be calculated based on the loss, and generator will update its weights, and eventually the generated speech will be generated speech feature will become very similar to the real speech. And then we obtain something called Nash equilibrium state optimal discriminator, when the discriminator is unable to find whether the generated speech is coming from the original or it is basically a fake one, and then we call it a Nash equilibrium state. So it comes from the game theory subject, something called Pareto optimality adversarial learning approach, min max game. So I'm not going to very deep about the game theory, but yes, the basic adversarial learning mechanism of a min max game theory Nash equilibrium state is actually originated from the this game theory subject. And Ian Goodfellow just introduced this game theory approach into deep learning, the field of deep learning. And in 2024, when he published the GAN paper, and it just revolutionized the field of speech synthesis, then image synthesis, video synthesis. And this is exactly how we do this voice conversion. We have the source speaker speech X, then we have the target speaker speech. I assume that the model will generate the corresponding speech features, which looks similar to the Y or the target domain, and discriminator will keeps on discriminating Y hat and Y. And then based on this loss function, which is the minimization and maximization of this loss common objective function, it will come to a Nash equilibrium state when the Y hat will become very similar to Y, and then you can use the vocoder to resynthesis the or reconstruct the speech from the speech feature, reconstruct the audio from the speech feature. And this is how exactly GAN model works. So I guess the cycle GAN part I have to skip. I'm extremely sorry. Let me go to the, because otherwise I'm running out of time. So this is basically what voice conversion I just explained, and these two are is my work. I will share the PPT. You can go through my paper. Let me explain another field which is associated to the speech synthesis. It is called speaker anonymization. So in case of speaker anonymization, what we do is exactly the way I explained the voice conversion. We try to change the identity of the target source speaker speech, keeping the content as it is, to anonymize the speaker, such that the identity of the source speaker cannot be disclosed. And this is called speaker anonymization. So voice conversion models are primarily used for speaker anonymization, to anonymize the identity of the source speaker without changing the content of the speech. And this is one work that we did, and it was published in IIII workshop EAAI this year, where we worked on child speaker anonymization. And this is exactly the how statistical vocoders or statistical speech synthesis model works. So we just take the spectral envelope, and then we did a nonlinear transformation with a factor of alpha, and for pitch we accept the fundamental frequency, and then we again multiply with the 2 to the power n/12. It's called the semitone shift. So if you take a fundamental frequency, multiply with the power of 2 to the power 1, to the power 2, to the power 3, you can change the octave. So any fundamental frequency, you take any frequency, multiply with 2 or divide it by 0. I mean multiply with 0.5, this is 1/2, or maybe 2 square, 2 cube, so on. So this is actually taking the particular frequency into different octaves. So say for example, 1 octave frequency is f, multiply with 2, then 2f. So between f and 2f there will be, I mean, we can divide into 12 small categories, chunks, and this is named as semitones. So we can just take the frequency, multiply with the n/2. N/2 means number of semitone shift we want to do, then we'll get the corresponding frequency. And if you will multiply with directly power of 2 to the power 1 to the power 2 or something, then you will just do a octave shift. So here we didn't do any octave shift, but we did a semitone shift, and we changed the spectral envelope, and then we try to do this speaker anonymization. Let me, I mean, I'm not going into the table. This is one of our recent work. I'm going to play the maybe the demo page. So the problem is, again, I have to share the particular tab for this. Now let me play the sound. So this is the original speech.
Once there lived a shepherd in a village.
Then we did to apply two classical approaches or statistical speech synthesis method or vocoders, I would say. VTLN, vocal tract length normalization, that is changing the spectral envelope with some non-linear transformation, and then also changing the pitch with some semitone shift. And then we have a Macadam's coefficient, which is also a non-linear transformation. So let me play this too. So now our idea is, I mean, our basic objective was change the vocal speaker identity using some classical method and also some neural network or deep learning based method. So such that the prosody doesn't get changed and the naturalness remains as high as possible. So let me just play the sounds.
Once there lived a shepherd in a village. He was a Once there lived a shepherd in a village. He was a kind.
Once there lived a shepherd in a village. He was a kind and good.
So after doing this kind of applying different methods for voice conversion or the speaker anonymization, we found that when you use this classical method, then yes, distortion we have obtained, but still we can retain capable enough to retain the prosody information. But when you change the, I mean, use the pre-trained NSCLM method, neural audio codex based method for speech synthesis, we found that there is a high distortion in the prosody. And the quality also get changed. The reason was like it is trained with the adult speaker, not child speaker. But the main problem was the prosody was getting changed with NSL method. So one of the advantages of using this classical method is like you do not you can it a distortion. There is a very less distortion of the prosody, primarily at the pitch and intensity. However, if you take the NSLM method or neural network method, the one problem is the prosody or the pitch or the intensity information, energy associated with the different time frames will get changed. So this distortion appears. So this is one of the problem that the current, I mean, the current research paper, if you look through, then the researchers are trying to address this issue of prosody preservation. Then this is called speech enhancement, where we use these GAN-based methods to enhance the. I mean, given a noisy speech, our basic idea is to remove the noise in a way that it can clone or to generate the corresponding clean speech. So here also we use GAN-based methods quite a long time. And as you can see over here, say for example, this is the clean speech. So here, if you take a small, if you zoom out this small chunk, then you can see that here there is no distortion. However, for noisy speech, there appears some distortion. Using GAN model, it can capable enough to reduce the distortion as compared to the noisy one. So this is how GAN models can also be used for speech synthesis, speech enhancement. Then neural audio codec. Neural audio codec is not exactly speech synthesis, but it is like a compression technique like MP3 and then JPEG for image compression, and also in video compression you have MP4. So what the idea is, using GAN model, we can also do this audio. We can address the neural audio codec related issues. So we earlier used to use only vector quantization methods, but then using discriminator or multiple discriminators, and by introducing the adversarial learning mechanism, we can get rid of the issues that are there in the only vector VAE VQ model. So when you use the discriminator, we have an additional model to take care of different type of feature related information, how it is changing. And then if the model will the generator there is a VAE model over here, or VAE VQ model, or VQ VAE model over here. It calculates the gradients based on the feedback coming from the discriminator, and that actually improves the quality of the audio samples. So this is how GAN is also being used for neural audio codec. And this is the same neural audio codec how is used for speech synthesis. For voice conversion or speaker anonymization. So you can have a pool of speaker, the way I've just mentioned. So you can train the model, encoder decoder model, with a specific set of speaker, and then you can just use another foundational model like Hubert, WebLM, Web2Vec to condition the model with some semantic information. There is a content related or linguistic information, and then model will generate the corresponding speech in some specific targets, a source speaker, or the already seen speaker vocal features. So this is how neural audio codec based models are using this voice conversion. GAN models, a framework of the adversarial learning mechanism for voice conversion or speaker anonymization. So I'm not going to this foundational model, how this Hubert, Web2Vec, WebLMS model work. Rather, I've hyperlinked the papers. You can go through it. So Hubert, WebLM, Web2Vec, these are foundational model trained using self-supervised learning mechanism, and different layers of it actually contributes for different tasks. So that's why this SSL model can be used for different downstream tasks, not only for a specific task, and different layers of it contributes to different downstream tasks. And this is what I have shown over here from the same paper. And using specific layers, you can condition them different models to generate, say for example, to extract, say for example, acoustic features, semantic features, linguistic features, and then based on that you can condition, say for example, here in the neural audio codec, you have used this Hubert model to condition the model to semantic features, that is content related information, keeping the speaker from some pool of scene speakers. Then singing voice synthesis, I have a very limited time, I guess I'll take 5-10 minutes more. So in singing voice synthesis, exactly very similar to speech synthesis, text to speech synthesis. So instead of text, we also give music score. What is music score? Let me show you with the example. That is the problem, but I have to share every time.
This slider not change.
Yeah, so I was talking about this singing voice synthesis work. So in singing voice synthesis is very similar to text to speech synthesis, where unlike the text to speech synthesis where we only give the textual transcript and expect the model to generate the corresponding speech. In case of singing voice synthesis, we give music score. So how music score actually looks like. So in music score, as I mentioned, that we also give corresponding pitch associated with the particular phone. Instead of only giving lyrical content, we also give the pitch related information. And then we can use this singing voice, different generative models. Nowadays, diffusion models are primarily being used. We have also detailed work on the diffusion based singing voice synthesis. And diffusion model is bit different from this GAN models. In case of GAN model, I guess now you can see my screen. Yeah. So in case of GAN model, when we have a separate generator and a discriminator, in case of diffusion model, what we do, we have a single model, but it has a forward pass and backwards pass. In the forward pass, we keeps on adding noise to it. We take a multimodal distribution and make it a unimodal distribution, and then we use some neural network based model to reconstruct the multimodal distribution from the unimodal distribution. And there is something called score function. That score function is basically the gradient that directs the model to go to the particular direction, with the help of which the model actually can map or can get the direction from mapping from unimodal to again multimodal. So basic idea is to understand the skeleton of the distribution. In forward pass, we keep on adding the noises using the Markov chain or deterministic process of adding noise. For backward pass, what we do, we try to estimate what was the noise added. So if your estimation is very similar, I mean it is very correct, then we can condition the decoder, that is basically a neural network based model, primarily UNet model, to generate different type of spectrogram, or say for example if it is an image, so we can use it for generating different type of images. So this is how diffusion model actually helps us to get an idea about or get an explicit control on the information about the distribution or the skeleton of the distribution. So there is something called again flow matching, which is one step ahead of this diffusion. So in case of diffusion, as you can see over here, it doesn't follow a smooth trajectory. To follow a smooth trajectory, in case of flow matching, it is considered as X, your source domain and target domain. What is the shortest part, or the trajectory will be a straight line, the linear interpolation. So that's why linear interpolation is used instead of stepwise noise adding. They considered is that the input is basically the clean one and the target is basically a noisy one, and you can use a straight line and linear. You can do a linear interpolation directly, and if you then do the first order partial differentiation of ZT, you can get the velocity. So here the idea is find the velocity of the actual representation and then use some neural network model, V theta. V is basically the model, neural network model, and theta is the parameter to estimate the velocity. You have some target velocity, you use some neural network model to estimate the velocity instead of predicting the noise, the way diffusion does. So this is more or less similar to diffusion. The only thing is like here velocity term is used or considered for estimation of the loss. And this is one work that we did. Let me go to this model. So it's the singing voice synthesis model. I mean, it is the baseline model is Singer, where we use multiple additional components to extract the content related information using text encoder and phoneme encoder. Then we use style encoder model to extract the style related information, pitch related information using a pretend JDC model. And then we condition the denoiser with MART embedding, this is a musical feature embedding, and Indic Web2Vec, that is the contextual embedding. And then we obtain a better result than that of the existing baseline Deep Singer model. And then I would like to show you another work that we did using this diffusion based TTS. Let me share. It is my last slide, and I will show you some of the samples. So this is the ground truth I am playing, and then I'll show within diffusion model we have is for Hindi data we have condition the model with specific condition model with pitch and intensity such that it can generate the corresponding speech. So it is called explicit prosody control speech synthesis. So I'll just play you the sounds.
वे प्राचीन ज्ञान और आधुनिक विज्ञान को साथ साथ लेकर चलने की बात कहते हैं.
So this is the ground truth and this is the generated one. Sorry, this one.
वे प्राचीन ज्ञान और आधुनिक विज्ञान को साथ साथ लेकर चलने की बात कहते हैं.
Then this is a completely generated sample using a long sentence, a paragraph.
फिर मालकिन को यह सूचना देने के लिए वह बाहर दरवाजे पर आ गया. मालकिन आई और उसने नेवले के मुंह में खून लगा देखा तो उसने समझा कि नेवले ने बच्चे को मार डाला है.
Then I'll also show how you have condition using different explicitly based on the pitch, such that the expressiveness of the speech can be also be changed. So this is a ground truth.
मैं जीवन की राह में आगे बढ़ चला.
Now this is condition on the explicitly on specific changing specific part of the content. Sorry, specific part of the pitch associated to particular content.
मैं जीवन की राह में आगे बढ़ चला. वे संभवतः उसे कुछ इनाम देते और प्रेम शंकर से उसकी प्रशंसा भी कर देते. वे संभवतः उसे कुछ इनाम देते और प्रेम शंकर से उसकी प्रशंसा भी कर देते.
So as you can see, the prashansha bhi kar dete. So this is basically conditioned by the pitch associated with a particular phonetic content. So that is what we are trying to do that explicit control on the expressiveness of the speech. Then I have almost covered, I mean, all my slides. Unfortunately, I could not give you a very good theoretical depth of diffusion and GAN. It would be taken, I would take more, maybe half an hour more. But yes, you can mail me if I can personally can give you some idea about how theoretically this GAN model and diffusion model works. And the theory is not very difficult, but yes, there are many things you have to have an idea about in order to understand like what is the differential equation, what is stochastic differential equation, why it is called stochastic, I mean how the stochastic term is actually working here. And then comes this how the different divergence theories is actually helping here. Then optimal transport is another theory, comes from this the theoretical machine learning, which we use in order to use in terms of loss function like earth moving distance. Then there are like as I mentioned, there's the learning mechanism, like game theory based learning mechanism that you use in GAN. So you get a complete idea about theoretical base about all these things. You may have to explore a bit more. However, I have also linked my Medium blog, and in my Medium blog, and I also have a YouTube channel. I do not regularly upload, but I have given some of the basic content related information of GAN, so you can explore those things. In my PPT, all these things are been linked, hyperlinked. Yeah, thank you.
Yeah, if anyone having any questions, then you can ask now, or you can mail to direct to Sandeepan. So I can give you the mail ID of Dr. Sandeepan. So anyone interested to work this kind of work, you can start the basics, like theoretical things you have to cover, then you can contact to Sandeepan sir. He can help you, or you can contact to me also. I'm going to connect to the Sandipan.
Sir, I have a question.
Yeah.
Yes, Isa. Yeah.
So, like you spoke about a Python package called Parcel-Mouth or something.
Yeah.
So, is it like a Prat but in a Python version?
Yeah, I mean the wrapper. I mean the way Prat works is just Python wrapper on it. So if you use the Prat and then you can find the exact parameter for which you are getting the course. I mean the correct pitch, intensity, and formants. Then you can just condition the Parcel-Mouth accordingly. So in the function, you can pass the arguments according to your whatever correct information. Parameters that is found from Prat.
Okay, so and you spoke about phonetization, something like that. So is it like taking a speech and then it will convert it into phonetics?
No, it is not for phonimization. For phonimization, you have to use. I mean, if you want to use libraries, then eSpeak phonemizer is there. Epitren is a phonemizer. Then G2P phonemizer is there. Or you can have your. I mean, you can get any dictionary. You can get a dictionary where you can have words and corresponding phonemes, and then using the what will say some deterministic method, deterministic algorithm, you can do the phonimization. Given a new word, you can do the phonimization. But if you want to use only libraries, then eSpeak phonemizer is there, Epitren is there.
Can you please write?
Yeah, I can write it down here. What is the text? Yeah, deep phony. So it doesn't support all languages. You have to check which languages support.
Okay, that okay.
Deep phonemizer, Epitren, then eSpeak, and G2P. G2P is deterministic stick. And for Indian languages, I have used primarily IIT Madras PhoneSet. Yeah.
All right. Thank you, and thank you for the presentation.
Yeah. So I will share the PPT and all these things has
Yes,
been already.
Sandipan sir, I will share the recordings today only.
Okay.
I will upload and give the links to them so that there is no problem. If any one of you wants to connect to Sandipan sir, you can directly, or through me also you can connect. Any other questions? I think tomorrow we have 3 sessions. I think Govind sir, Murli, and Parasmita Bhai. 3 will take the class. Healthcare application, Govind sir will tell. Then LID by Murli, spoken language identification. Then speech rhythm analysis by Parasmita Bhai. The 3 sessions are there, so join on time. And I think Monora ma'am is here. From the beginning, lots of students are there. Ma'am, are you here?
Yes, sir. Good afternoon. Yes, I'm here.
Good afternoon.
Yeah. Nice.
So your session
talking
is
with
at
you.
last,
Yes, sir. Yes, sir. Thank you so much. I will be there.
When you'll visit Bhubaneswar, definitely try to meet with me.
Of course, sir. Of course. It's my pleasure and nice to talking with you. Of course, I will meet you.
Yeah. Yes. Okay, ma'am. Thank you, Sandipan sir.
Okay, thank you.
Okay. So we'll be in contact through the Jagabandhu only. Fine.
Okay, sure.
Sandipan,
Yes,
sir. And
ma'am.
Sandipan also it's a wonderful presentation, and I know him personally. So they are doing lots of work.
Thank you, ma'am.
Yeah.
Yes, from the message I got to know. Means from there only I came to know that you are here in the chat box.
Yes.
Actually, yeah. Parallelly, I am doing 2 things, that evaluation and this thing. That's why some students have messaged. I have not seen that one during that slide change. So that message I missed out. Anyway.
Yeah, it's happened. It's not a problem, but it was very nice. Yeah.
Yes, sir. Nice presentation.
Thank you so much.
Giving the good feedback.
So I just mailed you the PPT, so you can share later on.
Okay. I'll share the PPT as well as this recording. Also going to be shared today only.
Yeah.
Thank you. Thank you.
Thank you,
Thank you.
Monodama. Bye, man.
Thank you. Let us stop. Dr. Monodama, bye.
Yes,
Dr.
bye.
Sandipan, bye. Bye. Bye.
Bye.